Hi there, my name's Hamish Reid and I'm based at the University College London in the UK. Here to talk to you today about type 3 solar radio bursts. Now, type 3 bursts are probably the brightest astrophysical sources in the radio sky. They can reach fluxes of about 10 to the 9 Janskis, or even more. And their signatures of electron beams that are accelerated in the atmosphere of the sun can then propagate out along the coronal magnetic field out into the solar wind. You could see a LOFAR image of a type 3 burst in figure 1. The colored contours are the type 3 burst at about 80% level. Now, the type 3 burst frequency decreases as a function of time, and this is related to the electron beam propagating through plasma with a decreasing plasma frequency. Now, the type 3 burst can exhibit fine frequency structure that you can see in figure 2. There's a LOFAR dynamic spectrum there. And this fine frequency structure is believed to be caused by background electron density fluctuations, which modulate the Langmuir waves that are produced by the electron beam, which ultimately modulates the level of radio. But what nobody had done before was to create a theoretical model that linked the intensity of the fine radio structure to the intensity of the background electron density fluctuations. And we managed to do that analytically, and you can see the relation on your screen there. Now, to confirm this and explore it further, we combined LOFAR observations with our numerical simulations of electron beams propagating out through the solar corona and the subsequent radio emission they produce. And by analyzing the fine frequency structure, we found that the exciter velocity for these fine frequencies was around about 0.7 megameters per second, which compared very well with the Langmuir wave group velocity. And indeed, through the simulations, we found that it was the Langmuir waves moving that caused this fine structure. Now, because we know the Langmuir wave group velocity, we can then estimate the thermal velocity of the background plasma, which is really interesting because then we have an estimate of the temperature of the solar corona at altitudes you can't do in any other way. And because we know as well the thermal velocity, and we can estimate the electron beam velocity from the whole type 3 burst, we then are able to use the radio fine structure to estimate the background density turbulence. And again, this is a new technique that you're able to do for the background density turbulence at altitudes where you don't have any other way of estimating this. So it's a really interesting find. And if you want to know more, we've recently published our results in Nature Astronomy, and the link is below. Thank you.